Right now, somewhere in the Milky Way, there is almost certainly a star surrounded by planets. On one of those planets, there is almost certainly something alive. And whatever that something is, it may have looked up at the night sky and felt exactly what you have felt. That pull, that quiet certainty that it cannot be alone. That feeling is not irrational. The numbers demand it. 400 billion stars burn inside this galaxy alone. 400 billion. Beyond the edges of the Milky Way, there are roughly 2 trillion more galaxies, each carrying their own hundreds of billions of suns. The universe is not sparse. It is extravagant, almost recklessly so, as if whatever built this place overbuilt it by orders of magnitude beyond anything life could ever need. And somewhere in all of that, somewhere in that staggering, almost offensive abundance, there are minds, other minds, looking out, wondering the same thing you are wondering right now. Here is where the ground shifts beneath you. The universe was not built for meetings, not as a poetic observation, not as a philosophical caution, as a structural feature of physical reality. The subphysical laws that allowed stars to ignite and planets to cool and chemistry to crawl toward biology have also made certain, with something close to mathematical precision, that what they created will never find each other. The numbers that inspire the hope and the numbers that forbid the contact are the same numbers. That is not an accident. That is the architecture. So whatever you believe right now about alien life, that it exists, that contact is inevitable, and that we are simply waiting on better technology, hold that belief carefully. It is about to be used against you. We begin now. Start with a number that should fill you with hope. 400 billion. That is how many stars burn inside the Milky Way right now. As you sit here, as your blood moves through you, as your eyes track across a screen in a civilization that has existed for the blink of a cosmic eye. 400 billion fires, most of them older than the Earth, most of them surrounded by worlds we have never seen. But we know the worlds are there. We know because we looked. In 2009, we launched a telescope called Kepler with one very specific job: stare at a single patch of sky and watch for shadows. That is the whole method. When a planet passes in front of its star, as it dims the starlight by a fraction, 1/100th of 1%, a shadow smaller than the fluctuation of a candle flame seen from across a city, Kepler watched 150,000 stars for 4 years. 4 years. And what came back rewrote everything we thought we knew about how common planets are. They are everywhere. Conservative estimates now place the total planetary population of the Milky Way at roughly 1 trillion. 1 trillion worlds spinning in the dark around 400 billion suns. That number is so large, it stops meaning anything if you simply say it. So instead, consider what it would take to merely visit them, not study them, not land. Just pass by each one for a single second. 1 planet per second, or every second, without stopping. You would need 31,000 years, and not 31,000 years to visit a sample. 31,000 years to touch every single world in this galaxy for 1 second each. The Roman Empire rose and fell. The entire recorded history of human civilization, every war, every dynasty, every empire that ever consumed another, fits inside a fraction of that schedule. And at the end of it, you would have spent 1 second on each world and 0 seconds understanding any of them. That is your planetary tour. That is the itinerary. It is, honestly, the worst vacation ever conceived. And yet, and here is where the number gets sharper, not all of those 1 trillion worlds are candidates for life. Most orbit the wrong kind of star, too dim or too violent. Most sit at distances that would freeze or boil any chemistry before it had a chance to try. So we narrow the field. Roughly 20% of Sun-like stars host rocky planets sitting in what we call habitable zones, not too hot, not too cold. And the Milky Way contains somewhere between 10 and 20 billion Sun-like stars. Run that fraction against that population, and you land on somewhere between 2 and 4 billion worlds that sit in the right place around the right kind of star. 2 to 4 billion. That number should already be enough. That should be the end of the argument. 2 billion second chances, 2 billion shots at the chemistry that made you possible. But then you account for the red dwarfs. 70% of all stars in this galaxy are not like our Sun. They are smaller, dimmer, cooler, red dwarfs, and they host planets too, in abundance. 40 light years from here, or close enough to feel almost neighborly on cosmic scales, sits the TRAPPIST-1 system. 1 red dwarf, 7 rocky planets, at least 3 of them sitting in the range where liquid water is possible. 1 system, 40 light years, 7 chances. Multiply that kind of density across the hundreds of billions of red dwarfs packed into this galaxy and the number of potentially habitable worlds, including their planets, climbs toward 10 billion. 10 billion. Not 10 billion stars. Not 10 billion galaxies. 10 billion worlds in this galaxy alone, where the temperature is right, where a rocky surface exists, where water might pool rather than evaporate or freeze. 10 billion addresses where life is not forbidden by physics. 10 billion places where, if the right chemistry arrived at the right moment, something might begin to stir. And that is the peak of the hope. Sit with it for a moment, because the view from here is extraordinary. 10 billion possible homes, scattered across the dark, orbiting their patient stars, cycling through their seasons, cooling and warming and cycling again. Some of them have done this for longer than the Earth has existed. Some of them finished their first billion years before our solar system had even condensed from dust. Out there, right now, there could be an ocean reflecting a sun we have never named, a sky some other color, a silence not yet broken. 10 billion chances for that to be true. Hold that number in your mind, because what follows depends entirely on what you believe that number means. What you believe that number means is everything, because here is where the hope gets complicated. Our Earth formed 4.5 billion years ago, and within 800 million years of that, geologically, almost immediately, the earliest chemical signatures of biological activity were already present. Life did not wait. It did not take a long run-up. The planet cooled, the oceans settled, and chemistry became biology with what looks, from a distance, like impatience. That fact is not small. It suggests that the step from raw chemistry to living systems is not the hard part. Given the right ingredients and enough time, life may not be a miracle at all. It may be something closer to inevitable. But intelligence is a different question entirely. In 1961, an astronomer named Frank Drake sat down and tried to turn that question into arithmetic. His equation was not a precise measurement. Yes, it was a framework, a way of forcing every assumption about life and civilization into the open, so you could at least see where your uncertainty was hiding. Run the variables that matter. How many stars are forming? How many host planets? How many of those planets sit in the right temperature range? How many develop life? How many of those develop intelligence? How many build technology? How long that technology lasts? Multiply them together, and what falls out of that chain of probability using moderate estimates, not pessimistic ones, not optimistic ones, but deliberately moderate, is roughly 10 civilizations, active, right now, in this galaxy. 10. That number sits there, and it does not feel like abundance. It feels like a verdict. But let's take it seriously, because the number is only half the problem. And the other half is the arena. The Milky Way stretches 100,000 light years from edge to edge. Its disk is roughly 2,000 light years thick. When you calculate the total volume contained inside that shape, you arrive at something that doesn't pass easily as a number. 15 trillion cubic light years. 15 trillion. That is the space in which your 10 civilizations are floating. That is the ocean. So distribute 10 civilizations across 15 trillion cubic light years. Give each of them an equal share of that emptiness. Then ask, on average, how far is the nearest one to you? 11,600 light-years. Say it slowly and let the distance register. 11,600 light-years. Light. Our traveling at 300,000 kilometers per second, the fastest anything in this universe is permitted to move, would need 11,600 years just to cross that average gap between neighbors. Not round trip, one way. A radio signal, the absolute cheapest communication we know how to send, dispatched today, would arrive at the nearest civilization's address in 11,600 years. Their reply would reach us 23,000 years after we sent the first word. 23,000 years. The entire span of recorded human civilization could collapse and rebuild several times over inside that silence. That is not a communication delay. That is not lag. That is the effective severing of any possible relationship between two minds. And 10 is not even a pessimistic estimate. 10 is moderate. And so push generosity further. Assume there are 80 civilizations out there, 8 times more than the moderate position. At that density, the average nearest neighbor is still 5,800 light-years away. That round-trip signal delay is still longer than the distance from now back to the beginning of written language. Keep pushing. Assume 1,000 civilizations spread across this galaxy right now, all of them burning with technology and intent. Even then, the average gap between neighbors is 2,500 light-years. The nearest star to our sun is 4 light-years away, and we have never gone there. 2,500 light-years is so far beyond that comparison, it barely registers as the same category of number. So think about where that leaves us. Not 10 billion habitable worlds, and not the abundance. The real number, the number that matters, is the distance between the things that actually developed the capacity to wonder. And even when you fill the galaxy with 1,000 of those things, the math still places the nearest one over 2,000 light-years away. The hope did not disappear. It just changed shape. 10 billion addresses where life is not forbidden becomes, after the full chain of probability runs its course, a handful of isolated minds scattered across a volume so vast that the distance between any two of them is measured in tens of thousands of years of light travel. Not distance in the way you drive a distance. Distance in the way a castaway on a remote island is distant from the nearest shore, except the ocean is 15 trillion cubic light-years of vacuum, and there are no boats, and the shore might not even be looking. 11,600 light-years. That is the average gap, and that is the number the math returns when you take the most charitable, reasonable assumptions and press them all the way through. But that number is still abstract. 15 trillion and 11,000 and 2,500. These are combinations of syllables, not felt realities. The human brain did not evolve to process light years. It evolved to navigate a savanna, to estimate whether the river was crossable, to judge whether the storm on the horizon would reach camp by nightfall. These distances are outside of anything your nervous system has a direct reference for. To ground these distances in something the human brain can attempt to process, consider an analogy. Here is the analogy. Shrink the Milky Way, all 100,000 light-years of it, all 15 trillion cubic light-years of volume, down to the size of the continental United States, coast to coast, roughly 3,000 miles. Every star, every planet, every cubic inch of interstellar gas compressed into that footprint. At that scale, our entire solar system is smaller than a grain of pollen, not a pebble, not a speck of dust, smaller than pollen. And Proxima Centauri, the nearest star to our sun, the closest thing we have to a neighbor in the real universe, sits 4 inches away from us in this shrunken version. 4 inches, the length of your thumb. You could reach it without moving your feet. And in this analogy, we have been unable to go there. Now take the 10 civilizations the Drake equation returns as a moderate estimate. Scatter them randomly across that 3,000-mile span, New York to Los Angeles, Canada to Mexico, the full expanse. 10 people, 10 minds, 10 lights in the dark. On average, the nearest person to you is 900 miles away. That is roughly the distance from Chicago to Denver. Open terrain, no roads, no vehicles, no way to send a message that arrives in less than years of walking. You can shout. The sound will not carry. You can light a fire. No one will see it. You are 900 miles from the nearest other person on a continent with no infrastructure connecting you to them. And the continent itself is suspended in empty space with nothing outside its borders in any direction. That is what the galaxy looks like to us right now. Not metaphorically, not approximately. That is the actual structure of our situation, is scaled to something your nervous system was built to navigate. And 900 miles in the analogy is 11,600 light years in reality. Say that again, without the analogy softening it. 11,600 light years. The distance a beam of light, traveling at 300,000 kilometers per second, the fastest anything in the universe can move, would need 11,600 years to cross. Not 11,600 miles. 11,600 years of light travel. That is the gap between us and whatever is closest. Here is what that means for conversation. You send a signal today, a radio wave moving at the speed of light, the only kind of message we know how to send across interstellar space. That signal reaches the nearest civilization in 11,600 years, and they receive it. They reply immediately. Their reply travels back at the speed of light. It arrives here 23,000 years after you sent the first word. 23,000 years. You will not receive the reply. Your children will not receive it. Every civilization that has existed in recorded human history will have risen and collapsed before the answer comes back. Whatever question you asked will have been forgotten for longer than writing has existed by the time the response arrives. That is not a conversation. That is not even the ruins of a conversation. It is two people shouting into opposite ends of a tunnel so long that neither one will live to hear if the sound ever reached the other side. So the radio silence we sit inside is not a puzzle to be solved by pointing a bigger antenna at the sky. It is physics. It is geometry. Distance so large that even the fastest possible signal cannot bridge it within the span of anything we would recognize as a civilization. We are not failing to hear them because our instruments are too crude. We are not failing to hear them because they are not transmitting. We may be failing to hear them because 11,600 light years is a gap that makes even light feel slow. And that is the last remaining comfort gone. Not the comfort of numbers, which collapsed when 10 billion habitable worlds became 10 isolated minds. Not the comfort of proximity, which collapsed when 11,600 light years became 900 miles of impassable terrain on a shrunken continent. Now the comfort of communication is gone too. The idea that even if we could not go there, we could at least talk, that across the void there could be some exchange of signal and reply, some thin thread of contact stretched across the dark. 23,000 years severs that thread before it is ever tied. You are sitting on a continent with 9 other people 900 miles away in every direction. You cannot reach them. You cannot signal them. The gap is not an engineering problem waiting for a better solution, but the mind does not stop there. The mind asks the next question. It always does. It asks, what if we went anyway? Not a signal, not a radio wave. What if we built something and crossed the distance ourselves? What if we simply went? Now restore the galaxy to its actual size. Replace miles with light years. Replace open terrain with hard vacuum, with temperatures near absolute zero, air with radiation that strips apart anything biological, with distances so vast that the nearest star to our sun sits not 4 inches away on a shrunken map, but 4 light years away in the actual universe. And we have never once crossed even that. What happens when you try? What happens when you try is this. you discover that the void is not empty. This is the part that gets me. The void is not empty. It is armed. The way we picture interstellar space, the way every film has trained us to picture it, is as a clean, dark nothing. Stars in the distance like fixed lights on a black ceiling, and between them, silence. The ship cuts through it smoothly, instruments humming, the crew eating dinner, because there is nothing out there to interrupt a voyage. That image is wrong in a way that matters immediately and fatally. They start with the air around you right now. Every cubic centimeter of the room you are sitting in contains roughly 25 billion molecules. That number is so large it resists comprehension. The best vacuum a laboratory on Earth can produce gets that down to about 10,000 molecules per cubic centimeter. Still, 10,000. Even our most controlled, deliberate attempt to manufacture emptiness leaves 10,000 particles per cubic centimeter behind. Now consider interstellar space, 1 atom per cubic centimeter. Not 10,000, not 1,000, 1. On average, across the vast stretches between stars, there is 1 atom per cubic centimeter. Hydrogen mostly. Alone. You would need to travel kilometers to collect enough matter to fill a thimble. And so the mind concludes, nearly nothing. Safe, crossable. But the dust does not care what the mind concludes. Scattered through that near vacuum, at a density of roughly 1 grain per 100,000 cubic meters, are particles of microscopic dust, silicate grains, carbon compounds, frozen molecular fragments left over from dead stars. You cannot see them. No instrument on a spacecraft would pick them up until they were already through the hull. At the speeds a spacecraft moves today, tens of kilometers per second, these grains are a nuisance. At the speeds you would need to cross 11,000 light-years within anything resembling a human lifespan, they become something else entirely. Take 1 milligram of dust, a grain so small it would be invisible to your naked eye. Accelerate it to half the speed of light, half of 300,000 kilometers per second, and let it meet a spacecraft head-on. That impact releases the energy equivalent of 3 tons of conventional explosives. From a particle you cannot see, from a grain smaller than a human cell, at half the speed of light. Now pushed to 90% of light speed, the kind of velocity that starts to make interstellar travel feel even remotely plausible over human timescales. That same invisible grain hits like 25 tons of TNT, 25 tons, from nothing, from empty space. And here is what makes this different from every other engineering problem we have ever faced. It is not a single obstacle you identify and solve before departure. It is continuous. The dust is everywhere, distributed across the entire path, and the faster you travel, the more devastating each encounter becomes. You are not dodging bullets. You are flying into a permanent, invisible storm of them at speeds where each bullet carries the destructive energy of a bomb. The shielding required to survive this is not a solved problem with a known cost. Any shield thick enough to absorb impacts at those velocities becomes so heavy it demands more energy to accelerate, which requires a larger fuel source, which adds more mass, which demands yet more energy. Every attempted solution compounds the problem it was meant to solve. And the radiation does not wait for an impact to kill you. Interstellar space is permeated with cosmic rays, high-energy particles streaming from supernovae and distant galactic events. And at relativistic velocities, the craft's own motion transforms the sparse interstellar medium into a continuous radiation bath. Biology degrades. Electronics degrade. Over the decades, such a voyage would require even under the most optimistic projections. These are not manageable hazards. They are a countdown. So you are trapped between 2 lethal facts that push in opposite directions. To cross the distance in anything resembling a navigable time, you must go fast. But the faster you go, the more kinetic energy each dust grain carries when it meets you. Speed is not the solution to the problem of distance. Speed is a second problem stacked on top of the first, and it grows worse the harder you try to solve the original one. The void is not waiting to be crossed. It is waiting to destroy whatever crosses it. And it is in that slender gap between almost and certainly that the next barriers reveal themselves. Because distance alone, however vast, is theoretically a problem of patience and engineering. You could imagine, if you stretch the imagination far enough, some civilization with enough time and enough resources and enough tolerance for suffering building something that survives the gauntlet. Some hardened vessel, some shielded probe, some machine patient enough to cross the dark. You could almost convince yourself that the physics, brutal as it is, it does not absolutely forbid arrival. Not quite. Not yet. But the speed required to make that crossing in any meaningful window of time runs into something else. Something that is not an engineering barrier at all. Something that sits not in the metal of a hull or the calculation of a shield, but in the structure of reality itself. The universe has a speed limit, and the closer you approach it, the stranger the universe becomes. And the speed limit is not what most people think it is. When people hear that light travels at 299,792 kilometers per second, they file it under very fast. They think of it the way they think of a highway speed limit, a posted number, a rule, something that exists outside the object rather than inside it. Something you obey or don't obey, depending on what you're driving and how brave you feel. That intuition is wrong, not slightly wrong, fundamentally wrong, in a way that closes off the last exit from the trap we've been building. In 1905, Albert Einstein published Special Relativity, and what it says, stripped of mathematics, is this: the speed of light is not a rule posted on the road. It is a structural property of space-time itself, and the universe enforces it not by pulling you over, but by making it physically impossible to reach. Here is how it enforces it. Every object with mass, any mass at all, resists acceleration more and more the faster it travels. Not because of friction, not because of fuel running out, because its effective mass increases. The technical term is the Lorentz Factor, yet you do not need to know the term. You need to know what it does. At 50% of the speed of light, your effective mass is already 1.15 times your resting mass. Not dramatic yet. You are heavier, but manageable. Push to 90% of light speed, and your effective mass more than doubles. A Lorentz factor of 2.29. Every kilogram of your ship now resists acceleration as though it were 2¼ kilograms. And you haven't moved the ceiling at all. It is still there, unchanged. Now push to 99.9%. Your effective mass is 22.4 times what it was at rest. The same ship, the same atoms. But the universe is now treating each kilogram as though it weighed 22. And here is the part that should unsettle you. The ceiling is still the same distance away. A light speed is still exactly as far above you as it was when you started. You have spent an almost incomprehensible amount of energy to close a fraction of the gap, and the gap to the limit has not narrowed by a single meaningful step. The closer you get, the heavier you become. The heavier you become, the more energy you need to accelerate further. And as your speed approaches light speed, the energy required approaches infinity. Not a very large number, not a number we haven't figured out how to reach yet. Infinity, an infinite amount of energy to move any object with any mass at any finite fraction of that ceiling. The universe is not asking you to go faster. It is telling you that no engine, no civilization, no physical process in existence can make a massive object reach that speed, ever. This is not a wall you can eventually build a door through. This is a wall whose thickness increases the closer you get to it, and which becomes infinite at the surface. The brick wall of the speed limit is not a suggestion. It is a wall with teeth. The closer any massive object approaches it, the more violently the universe pushes back. And we know this is real. This is not theory waiting for confirmation. The Large Hadron Collider accelerates protons to 99.9 0.9999991% of the speed of light. Those protons are not theoretical. They are tested, measured, and they behave exactly as the Lorentz factor predicts. Heavier, harder to push, demanding more energy with every fraction of a percent gained. That the GPS satellites in orbit above you right now require a relativistic correction built into their software. Without it, they would drift by 10 kilometers per day. Not because the engineers wanted to be clever, because the satellites are moving fast enough that time itself runs differently for them. And if you ignore that, your map lies. Relativity is not a thought experiment. It is operational engineering. It runs in your phone. But here is where this bends in a direction you might think offers an escape: time dilation. At high speeds, time for the traveler slows down relative to the universe around them. At 50% of light speed, the traveler experiences time at 87% the rate of someone stationary. At 90%, that drops to 44%. At 99% of light speed, and the traveler is only living through 14% of the time an outside observer would count. 20 ship years at that speed correspond to 143 years passing outside. So you might think, fine, a traveler cannot reach light speed, but they can get close enough that the journey feels short to them. 20 years to cross what the universe counts as a century and a half. And that is true for the traveler. But think about where that leaves the civilization that sent them. The society that built the ship, loaded the crew, watched it leave. They wait 143 years before hearing anything. And that is at 99% of light speed, and a velocity that demands energy inputs we have not begun to approach, and that still condemns every person who waved goodbye to die long before the traveler arrives. The traveler experiences a compressed journey. Everyone else experiences the full geological weight of the wait. Time dilation is not a solution to the problem of distance. It is a private shortcut that abandons everyone else at the station. And even this, even the partial mercy of the traveler's compressed time, comes at a cost that hasn't been named yet, because you cannot simply decide to travel at 99% of light speed. You have to get there. You have to accelerate a ship, a crew, a payload, across the enormous gap between standing still and that velocity. And what the Lorentz factor means in practice is that the energy required to push any meaningful mass toward that ceiling is not merely large. It is a number that starts to make the distances themselves look modest by comparison. So let us name the number: a payload of 1,000 metric tons. That is roughly the mass of a naval destroyer, a serious vessel, built for war, loaded with crew and equipment. Not a generation ship carrying thousands of people. Not a colony ark. A destroyer. Minimum viable. Modest by any reasonable interstellar ambition. And we want to accelerate it. Our fastest probe right now is New Horizons. It is moving at 16 kilometers per second. We are proud of that. It took decades to build, and a Jupiter flyby to fling it that fast. And it will reach the nearest star system in roughly 80,000 years. 16 kilometers per second. 1% of light speed is 3,000 kilometers per second. That is not a refinement of what we can do. It is not the next step. It is a different category of achievement entirely. But let us start there. 1%, the gentlest rung on the ladder. To push our destroyer payload to 1% of light speed requires 4.5 times 10 to the 18th joules of kinetic energy. That number needs a translation. The Tsar bomber was the largest nuclear weapon ever detonated, a device so violent that it shattered windows 900 kilometers away. 1% of light speed for our payload costs the energy of 20 Tsar bombers, for the gentlest rung, for a velocity so low that crossing 11,600 light-years would still take over 250,000 years. Hold that. 20 nuclear detonations of the largest weapon humanity ever built, and you are not even close to useful. Now step up, 10% of light speed. The kinetic energy required climbs to 4.5 times 10 to the 20th joules. That number has a name in human terms. It is the total energy output of human civilization for an entire year. Every power plant running, every engine burning, every solar panel catching light, every dam turning for 12 consecutive months, poured entirely into this one acceleration event for one ship, reaching a speed that would still take 25,000 years to cross the distance between us and the nearest likely civilization. That is the second rung, 30% of light speed. The energy requirement reaches 4.3 times 10 to the 21st joules. 7 years of all human energy production, not 7 years of building toward it. 7 years of total output, every joule redirected, every other use of energy on the planet suspended, every hospital and city and factory running dark while the ship accelerates. 7 years of civilization traded for a journey that still spans 8,000 years of travel time. 8,000 years. The pyramids of Giza are roughly 4,500 years old. The ship launched at 30% of light speed would still have nearly 2 of those spans left to travel when it arrived. 50% of light speed. Now the number becomes 24 years of total human energy output. 2.5 decades of everything humanity can generate. And here is where this stops feeling like engineering and starts feeling like a verdict. And because 50% of light speed is the speed at which time dilation begins to offer a traveler any meaningful compression of experienced time. It is the threshold where the journey becomes survivable within a human lifetime, for the person on the ship at least. And reaching it costs a quarter century of civilization's entire productive energy. That last sentence deserves a pause. 24 years of everything for one ship, and we are not finished climbing. 90% of light speed. The kinetic energy required is 1.6 times 10 to the 22nd joules. 200 years of total human energy output. Not 200 years from now, when our civilization might be larger and more powerful. 200 years of output at current levels. Today, right now, the civilization that exists on this planet, everything it can produce across a span longer than the United States has existed as a nation, fed into a single acceleration, for a single ship, toward a destination 11,600 light-years away, that it would still take nearly 3,000 years to reach. And it gets worse, because every number just given, every Tsar Bomba comparison, every year of human output, every devastating rung on that ladder, describes only the kinetic energy already contained in the payload when it is moving. It describes the energy state of the mass when it arrives at speed. It does not ask where that energy came from. It does not count the engine. It does not count the reactor. It does not count the fuel. And this is the point where the problem does not just get harder. This is where it changes shape. And because the fuel that generates the energy to accelerate the payload must itself be carried aboard the ship, and it must therefore itself be accelerated. Every kilogram of fuel you load is a kilogram that requires more fuel to move, which requires more fuel to move that fuel, which requires more fuel to move that fuel's fuel, compounding without mercy from the first moment of ignition to the last. The payload is not the thing being accelerated. The payload is merely what survives the arithmetic. The payload is merely what survives the arithmetic. And now we have to count the arithmetic. The rocket equation is a compounding problem. It was derived by Konstantin Tsiolkovsky in 1897, and in the more than a century since, nobody has found a way around it. Not because we haven't tried. Because the equation is not describing a limitation of our engineering. It is describing a limitation of the universe. The logic is this. To accelerate a mass, you burn fuel. But that fuel has mass. So you must also accelerate the fuel, which means you need more fuel to move the fuel, which means you need more fuel to move the fuel that moves the fuel. Each layer of the problem generates a new, larger version of itself. The recursion does not converge. It compounds. And at the speeds we are discussing, the speeds required to cross 11,600 light years within any meaningful span of time, it does not compound gently. At 50% of light speed, the fuel-to-payload ratio required by the rocket equation reaches 200 million to 1. Hold that ratio. At 200 million kilograms of fuel for every single kilogram of payload. Our ship carries a payload of 1,000 metric tons. That is 1 billion kilograms. Multiply by 200 million. The fuel mass required is 200 quintillion kilograms. For reference, a large asteroid, the kind that ends geological eras, might mass a few trillion kilograms. The fuel requirement for a single ship at 50% of light speed exceeds the mass of large asteroids by a factor of tens of millions. This is not an engineering challenge. This is a structural feature of the physics. The recursion has consumed the mission, but that number assumed something generous. It assumed you could extract every joule of energy sitting inside your fuel with perfect efficiency. No engine does that. No engine ever has. Actually, as that number isn't quite right, it's worse. That calculation assumed perfect efficiency, which no engine achieves. Every real propulsion system loses energy to heat, to exhaust velocity limits, to mechanical reality. So every ratio just described is a flaw. The actual requirement is higher. The compounding compounds. Now, consider what that means for the best propulsion technology we have ever seriously designed. In the 1970s, a team of British engineers worked for 5 years on a project called Daedalus. The goal was modest by interstellar standards. A flyby mission. No deceleration, no landing, no return. Just reach another star and observe it as you pass through its neighborhood at speed. The fuel they chose was deuterium and helium-3, the most energetically promising fusion reaction we can describe on paper. Helium-3 fusion converts roughly 0.4% of its fuel mass directly into energy. Not 1%, not 10%, 0.4%. The rest of the mass goes nowhere useful. It is inert exhaust. With that fuel, with that reaction, using 50 years of optimization, the Daedalus design settled on a target speed of 12% of light speed. The fully fueled ship would mass 54,000 metric tons. The payload it carried was 450 tons. That is a fuel-to-payload ratio of roughly 120 to 1. And that is for 12% of light speed, with no stopping. 12%. Not 50, not 90. 12. And even at 12%, yes, the journey to the nearest potentially inhabited system, 11,600 light years, would take nearly 100,000 years. And the ship flies past. It cannot stop, because stopping requires the same energy as accelerating. If you want to decelerate from 12% of light speed to 0 at the destination, you need to carry all the fuel for that deceleration too, which must itself be accelerated, which requires more fuel. The recursion restarts at the moment of arrival. A flyby is not a visit. A flyby is a photograph taken through a car window at highway speed. So 0.4% mass-to-energy conversion leaves us stranded. The equation demands better fuel. It demands fuel that converts more of itself into thrust. Far more. The logical question is, how high can that conversion rate go? Chemical rockets convert a fraction of a percent of fuel mass into energy. Fusion gets to 0.4%. What is the theoretical ceiling? What is the best any fuel can possibly do? The answer is 100%. Total conversion of mass into energy. And there is only one known reaction that achieves it. Matter meeting antimatter. Annihilating completely, releasing every joule locked inside both masses with nothing left over. That is the ceiling. Not fusion, not any refinement of fusion. Antimatter annihilation is the last door that the physics leaves open for brute force propulsion. And the question is no longer how much fuel we need. The question is what it would actually take to build it, to make the fuel itself real. That question has an answer, and the answer is its own kind of verdict. And so the last door swings open. Antimatter. Total conversion. 100% of the fuel mass becomes energy. Nothing wasted, nothing left over. The most efficient fuel that the laws of physics will ever permit. If anything can break the recursion, this is it. This is where the argument should finally reverse. This is where the math relents. It does not relent. Here is where you have to hold a specific number in your mind. In the entire history of human particle physics, every accelerator ever built, every collision ever staged, every experiment run at every facility on Earth since we first understood what antimatter was, we have produced a total of 20 nanograms of it. 20. A nanogram is 1/1,000,000th of a gram. A single grain of table salt weighs roughly 60,000 nanograms. The entire output of human civilization, every machine we have ever pointed at this problem, has produced less than 1/3,000th of a grain of salt. That is not a manufacturing bottleneck. That is not a problem of scale that more funding solves. That is the honest shape of the gap between what the physics permits and what reality provides. We don't really know if this is solvable. That's the honest answer. 20 nanograms in the entire history of particle physics. Not 20 grams, not 20 milligrams, nanograms. And the physicists who produced them were not trying to make fuel. They were trying to understand the structure of matter itself. The antimatter was a byproduct of science, not a product of engineering. Nobody was optimizing for yield. And even if they were, the situation gets worse before it gets better. Because making antimatter costs more energy than the antimatter contains. Read that again slowly. Manufacturing antimatter requires more energy than the antimatter itself will release. You put in more than you get out. Every gram of antimatter you create demands a greater quantity of energy to produce than that gram will return when it annihilates. Which means antimatter is not a fuel source. It is an energy storage medium, and a lossy one. You are not generating propulsion energy from antimatter. You are converting energy from somewhere else, spending more of it in the conversion than you recover, and storing the remainder in a form that is extraordinarily dangerous and extraordinarily difficult to contain. The 100% conversion efficiency is real, but the price of manufacturing what you burn is higher than what the burning gives back. And here is where the rocket equation arrives again, carrying its full weight. Even if we imagined, for a moment, that we somehow solved the manufacturing problem, that some future civilization had access to the raw energy to produce antimatter at scale, the rocket equation does not pause to acknowledge the achievement. And the same recursion that consumed every other propulsion scheme closes around antimatter too. To reach 50% of light speed with a payload of 1,000 metric tons, you need a fuel-to-payload ratio of 200 million to 1. Antimatter does not dissolve that ratio. It is the best-case version of it. 200 million to 1 is what you get after you have already assumed perfect fuel. That is the flaw with antimatter. With anything less efficient, the ratio climbs higher still. So where does the energy come from? Not from the ship. You cannot carry the energy needed to manufacture your own fuel. That would require still more fuel to carry the manufacturing energy, which requires more fuel to carry that. And the recursion does not close. The energy has to come from outside. It has to come from something enormous. Something that dwarfs anything a civilization could construct and carry. The only objects that produce energy at the required scale without any engineering at all are stars. We are not speaking loosely here. The energy needed to manufacture enough antimatter to accelerate a vessel across interstellar distances is not large nation energy, or planetary energy, or even multiplanetary civilization energy. It is stellar. You would need to capture and redirect the output of a sun, not for years, not for decades, but for spans of time that start to look like geological epochs, just to fill the fuel tanks. And even then, the ship you are fueling still faces every other barrier that has already been described. The dust, the radiation, the time, the arrival at a destination that may have changed entirely. during the crossing. Now, the physics has done something cruel here. It has made the perfect fuel real. It exists. Antimatter is not hypothetical. We make it, we observe it, we understand exactly what it does. The universe is not withholding the concept. It is simply demanding a price for the substance that no civilization built on a single planet, or even a single solar system, could realistically pay. The door is unlocked. The universe just put it at the top of a staircase that requires a star to climb. So think about where that leaves us. Every propulsion system that carries its fuel hits the same wall. The better the fuel, the more precisely you understand how completely you are trapped. Antimatter does not escape the rocket equation. It just makes the trap cleaner, the ceiling clearer, the verdict more precise. You carry fuel and the math devours you. Every time, without exception. But what if you didn't carry fuel at all? What if the energy came from somewhere else, not stored inside the ship, not manufactured before departure, but pushed from behind, continuously, across the dark? The ship would carry no propellant. The rocket equation would not apply. Nothing would need to be accelerated except the payload itself. The barrier that has closed every door so far is the barrier of carrying the means of your own motion. Remove that requirement and something changes. Something opens. The question is whether what opens is a road or just a different kind of trap. So what opens is this. Breakthrough Starshot is the name, and the concept is genuinely elegant. Instead of burning fuel on board, yet you build a laser on the ground or in orbit, and you fire it at the ship from behind. The ship carries no propellant, none. It is a sail, not a rocket. And the rocket equation does not apply because there is nothing to expel. The energy source stays home. The ship just catches the light and rides it. And it works. That is the part that matters. The project has serious physicists and serious money behind it. And the fundamental physics is sound. A 1-gram probe, lighter than a paperclip, illuminated by a laser producing 100 gigawatts of power, can be accelerated to 20% of the speed of light. 20%. That is faster than anything we have ever launched. It would reach the nearest star system in roughly 20 years. Not 80,000 years, not 100,000 years, 20. That is not nothing. And that is the single most promising number in this entire conversation. And it is real. But hold that number for just a moment, because the question is not whether a paperclip can reach another star. The question is whether anything living can. The moment you try to scale a laser sail to carry passengers, everything the elegance was built on collapses. A 1-gram probe is a chip of glass and a few nanometers of reflective coating. A crude vessel, the kind we have been discussing, roughly the mass of a naval destroyer, is 1 billion times heavier. The laser array does not scale linearly. The physics is remorseless. To push that kind of mass to a meaningful fraction of the speed of light requires an array producing not 100 gigawatts, but 100 exawatts. 100 exawatts. Every power plant currently operating on Earth, every dam and reactor and turbine, produces roughly 20 terawatts of electrical power combined. 100 exawatts is 5 million times that. You would need to build 5 million versions of our entire planetary energy infrastructure, point them all at the same ship, and fire simultaneously. That is the scale. Not a large laser. Not a very large laser. An engineering project larger than all of human civilization, by a factor that swallows human comprehension. And this is the moment where the rocket equation reappears, not as an equation you apply, but as the cage you thought you escaped. Laser sails were designed precisely to avoid it. No onboard fuel, no mass ratio, no staircase of propellant eating itself on the way up. And for 1 gram, that escape is real. Yeah, well, but the cage was never just about fuel. It was about energy. Total energy required to move mass across interstellar distances at useful speed. The rocket equation is the fuel version of that prison. The laser array requirement is the power version. Different walls, same cell. But there is something worse. something that does not get fixed even if you somehow built the array. The ship cannot stop. There is no laser at the destination. You would have to build one there before you sent the ship, which requires sending something there first to build it, which requires that something to stop, which requires... You see how this ends. Arriving at 20% of the speed of light with no way to decelerate. You do not land. You do not enter orbit. You pass through the target star system in hours. A bullet with no target. A crossing in the time it takes to eat a meal and then continuing into the dark forever. You can take photographs, you can transmit data, but you cannot stop and you cannot return. And nothing alive survives the deceleration that would be required to convert a 20% light speed transit into a rest. The fastest viable option for anything heavier than a postage stamp has just revealed that speed and arrival are not the same thing. So stand back and look at what we now have. Chemical propulsion falls short by orders of magnitude. The fuel required exceeds not just anything we could carry, but anything that physically exists. Nuclear fission, a step up, barely moves the needle at interstellar scales. Fusion, our most optimistic near-future technology, gets you a flyby after 100,000 years. Antimatter, at the best fuel physics permits, still demands stellar-scale energy just to manufacture. And now, laser sails, the one approach that sidesteps the fuel problem entirely. Real, funded, physically sound, work perfectly for probes the weight of an eyelash and become physically unreachable for anything that breathes. Every door has been checked. Every door is closed. Speed, it turns out, is not a technology problem in the way we want it to be. It is not waiting for a better engine or a smarter design or another century of physics. The barriers are not in the engineering. They are in the structure of the universe itself, in the way energy scales with mass, in the way mass resists acceleration, in the way the rocket equation compounds without mercy, regardless of what you burn or how you push. These are not obstacles, yet they are the shape of the rules. If the universe forbids speed, perhaps it permits patience. Perhaps the answer is not to go faster, but to simply go, slowly, deliberately, across timescales that dwarf everything a civilization has ever built or remembered or imagined. Perhaps the crossing takes not decades, but millennia, and something arrives on the other side that left so long ago the world that sent it has changed beyond recognition. Perhaps, but patience has its own physics and its own price. Patience, then. Slow travel. The only option left after the rocket equation killed every fast approach. The quiet, unglamorous idea that perhaps a civilization simply accepts the crossing will take a very long time and sends something anyway. No exotic physics required, no antimatter factories, no laser arrays the size of continents, and just thrust and time and the willingness to wait. So let's take patience seriously. Let's give it the numbers it deserves. 1% of the speed of light, 3,000 kilometers per second. That is not slow by any human measure. It is roughly 200 times faster than anything we have ever launched. And it is, critically, within the plausible reach of near-future propulsion. Not tomorrow, not this century perhaps, but not physically absurd. 1% of light speed is the kind of number serious engineers write in serious papers without embarrassment. At 1% of light speed, the journey to the nearest potentially inhabited star system, roughly 2,500 light years away, takes 250,000 years. Hold that. 250,000 years, not a typo, not a rounding error. 250,000 years of continuous travel, sustained thrust, functioning life support, navigational correction, structural integrity. 250,000 years from departure to arrival. And here is what that number means when you press it against everything humanity has ever done. All of recorded human history, writing, agriculture, the first cities, every empire that rose and fell, every war, every book, every scientific revolution, every name anyone remembers, fits inside the last 5,000 years. 5,000 years is 2% of that voyage. Your ship leaves Earth. Civilizations rise, they fall. Others rise. Rome appears and disappears. The Renaissance happens. The Industrial Revolution. The entire span of everything we have ever recorded. Everything we think of when we think of human history, all of it occurs in the final 2% of the journey. The first 98% of the crossing passes in silence. Before a single word was ever written down on Earth, that is where the weight of deep time becomes something different from a large number. It stops being arithmetic and becomes something closer to vertigo. 2%, every pharaoh, every philosopher, every scientist, every war, every invention, the last 2%. The ship has been traveling longer than our species has had language for nearly its entire flight. And that is the optimistic distance, the nearest plausible neighbor, given what we know about how rare technological civilizations are likely to be. If the nearest civilization sits 11,600 light years away, the conservative estimate from just 10 civilizations in our galaxy, then at 1% of light speed, the crossing takes 1,160,000 years, not 250,000, over 1 million. Recorded human history would fit into that voyage roughly 230 times over. But perhaps 1% is too conservative. Perhaps patience means accepting a longer journey, but a faster one. 10% of light speed, real fusion-level engineering, a genuine civilizational commitment. At 10% of light speed, the crossing to that 11,600 light-year destination still takes 116,000 years. More than 20 times the entire span of recorded human civilization. Also think about where that leaves us. Every version of patience arrives at the same answer. The journey outlasts everything we have ever built, remembered, or sustained. The fastest achievable slow crossing still dwarfs history. The most conservative distance still demands timescales that make our oldest institutions look like they were constructed yesterday and abandoned before breakfast. And institutions is the right word, because this is where the problem stops being about physics and starts being about something harder. A mission that takes 100,000 years is not an engineering problem. It is a civilizational commitment problem. Every space agency that has ever existed has been older than a few decades before it was defunded, restructured, deprioritized, or simply forgotten when the government that built it changed its mind. The longest continuously operating institution in human history, by most measures, perhaps a religious organization, perhaps a university, is a few hundred years old in any meaningful functional continuity, perhaps 1,000 at the outer edge in ceremonial terms. Against 100,000 years, 1,000 years of institutional memory is 1% of the mission. Against 1 million years, it vanishes entirely. But even this devastating combination of barriers does not tell the full story. Speed and energy address the question of whether a vessel can cross the gap. They do not address the question of whether anyone will be waiting on the other side when it arrives. But speed and arrival are not the same thing. And arrival, it turns out, is not the same thing as finding someone home, because the other side of this equation has been sitting quietly in the background, waiting to be addressed. We have been treating the destination as fixed, a civilization sitting somewhere in the galaxy, broadcasting, waiting, alive. And that assumption carries more weight than anything else in this entire problem. It may also be the most dangerous assumption we make. The Milky Way is roughly 13 billion years old. Not millions, billions. 13 of them. A number so large that the entire span of Earth's existence, 4.5 billion years, the planet forming from dust, life clawing its way into existence, everything that has ever lived and died on this world, fits inside it with room to spare. And for most of that 13 billion years, and nothing that could look back at the stars existed anywhere on this planet. multicellular life, organisms built from more than one cell, organisms with any internal complexity at all, arrived roughly 2 billion years ago. That sounds early. It is not. The galaxy was already more than halfway through its current age before anything on Earth had figured out how to be more than a single cell. Complex animals, creatures with skeletons and nervous systems, and the beginning of what would eventually become perception, appeared roughly 540 million years ago. Mammals arrived around 200 million years ago, warm-blooded, adaptable, fast-learning, and still 200 million years before anything in their lineage would point at a fire and understand what it was doing. Our genus, Homo, the lineage that leads directly to us, emerged roughly 2 million years ago. Modern humans, anatomically and cognitively recognizable as the thing reading this, appeared 300,000 years ago. And technological civilization, the ability to split atoms, send signals across space, launch objects off the surface of this planet, has existed for approximately 2 centuries. 2 centuries. Not 2,000, not 200,000. 200 years, give or take. That is the window. That is how long we have been the kind of thing that could, in theory, be detected. And here is what that means against the scale of the galaxy. If you compressed 13 billion years into a single calendar year, our entire technological civilization does not occupy a day, or an hour, or even a minute. Yet it occupies roughly 5/10,000ths of a second. A blink so small it does not register as a blink. It registers as nothing. Sit with that, not as a metaphor, as a structural fact about where we sit in time. Every satellite we have ever launched, every signal we have ever sent, every telescope we have ever pointed at the sky, all of it fits inside a sliver of cosmic time so thin it has no meaningful analogy. We are not a chapter. We are not a sentence. We are a single letter in a document 13 billion characters long, and we are not sure yet whether anyone will read it. Now consider what happens to civilizations, not what we hope happens, what the evidence on this planet alone suggests is likely to happen. 66 million years ago, a rock roughly 10 to 15 kilometers wide struck what is now the Yucatan Peninsula, the Chicxulub impactor. It did not merely kill animals, it restructured the dominant forms of life on the planet so thoroughly that mammals, previously small and hidden and marginal, were suddenly the inheritors of an emptied world. 75% of species vanished. An entire evolutionary experiment, hundreds of millions of years in the making, ended in what was, geologically speaking, an afternoon. This was not a rare event. The solar system is old and crowded and violent, and the craters pocking every solid surface in it are a record of how frequently the game resets. And that is only the external threat. We have now invented several ways to end ourselves from the inside. A sustained nuclear exchange, into a climate system destabilized past the point of agricultural recovery. A pathogen we engineer without understanding the consequences. We have been genuinely capable of some version of civilizational self-termination for less than a century, and the list of mechanisms has not gotten shorter. So what is a reasonable lifespan for a technological civilization? Nobody knows. The honest answer is nobody knows. But even the generous estimate, the deliberately optimistic, let them figure it out, assume they survive their own adolescence estimate, is roughly 1 million years. A civilization arises, develops, perhaps spreads locally, and eventually ends, for whatever combination of internal or external reasons. 1 million years, start to finish. 1 million years sounds long. It is not. 1 million years is 1/13,000th of the galaxy's age. It is 0.008% of the time that has elapsed since the first stars began forming in this galaxy. A civilization that lasts a full million years occupies a window so narrow against the backdrop of galactic history that finding it would require arriving at almost exactly the right moment. Not within 1,000,000 years, not within 100,000 years, but close, cosmically close. And that is before accounting for the journey time. At 10% of light speed, the speed we already established requires near civilizational levels of engineering commitment. The crossing to the nearest plausible neighbor takes 116,000 years, and that is more than 10% of a civilization's entire assumed lifespan, spent in transit before a single word is exchanged. So the question that has been building underneath all of this finally has to be asked directly. If a civilization's window of existence is 0.008% of galactic history, and another civilization's window is the same, what are the odds that those two windows overlap at all? Do the math. 1,000,000 years against 13 billion. Each civilization occupies 0.008% of galactic history. If you place two windows that size randomly on a 13 billion year timeline, the probability that they coincide, that they share even a single year of simultaneous existence, is roughly 1 in 6,500. 1 in 6,500. Not 1 in 100. Not 1 in 1,000. 1 in 6,500. That number needs a moment. This is not the probability of making contact. This is not the probability of exchanging signals. This is simply the probability that two civilizations exist at the same time, before anyone has traveled anywhere, before any message has been sent, before any engineering problem has been solved. Just the raw likelihood that two windows of intelligent life, each a generous 1,000,000 years long, happen to open during the same era of a galaxy that has been running for 13 billion years. 1 in 6,500. And here is what that number actually means. For every 6,500 civilizations that ever existed in this galaxy, only one pair would exist simultaneously. While the other 6,499 would spend their entire existence alone in time, separated not by distance, but by the simple fact that one burned out before the other ignited. The universe does not need to make travel hard to isolate civilizations. It can just run the clock. But say you beat it. Say the odds collapse in your favor. Two civilizations separated by 11,600 light years. That distance, again, the one we keep returning to, happen to be alive at the same moment, the same era. Their windows overlap. What does the journey actually cost? At 10% of light speed, the ceiling we established requires near civilizational engineering commitment. Because the rocket equation alone walls off anything faster for a crewed vessel carrying real mass. The crossing takes 116,000 years. Hold that number against the other one. 1,000,000 years total lifespan. 116,000 years one-way travel time. That is more than 10% of the entire civilization's existence spent in transit before a single exchange occurs. Not 10% of a century. Not 10% of a human life. 10% of everything. 10% of the full arc from first radio signal to last recorded thought, consumed by a single journey before arrival. And that is if the windows still overlap when the ship gets there. They started overlapping when the journey began. 116,000 years later, how much of that overlap remains? And now imagine a building, 10,000 apartments across 500 floors. Each tenant occupies their unit for 15 minutes out of every year, arriving at a random time, staying for their 15 minutes, and then going dark for the remaining 51 weeks. You move in, you live there for decades. The building is never empty. Statistically, someone is always present somewhere inside it. But the timing of each tenancy is independent, scattered randomly across the year. You could knock on every door on your floor every single day and find nothing but silence. Not because your neighbors do not exist, because their 15 minutes and your 15 minutes have never landed on the same afternoon. The building is full of people you will never meet because the schedule does not cooperate. And that is what temporal isolation looks like from the inside. Not loneliness, not distance, just two windows in an enormous building, never opening at the same time. And the cruelty is this: from inside your own window, everything feels present and vivid and real. Your civilization is alive. Your telescopes are running. You are searching. The building feels full of potential, but the tenants whose windows already closed left no forwarding address, and the tenants whose windows have not yet opened do not exist to receive a signal. The mail has nowhere to go. The building is simultaneously full of history and empty of anyone present. 11,600 light years. It has appeared in this argument before, as a measure of loneliness, as a measure of energy expenditure, as a measure of travel time. And now it functions as something else. It is the temporal executioner, the distance that, at the fastest plausible speed, devours 10% of your civilization's entire lifespan in a single crossing. It does not merely separate civilizations in space, it eats the time they had. So think about where that leaves us: 1 in 6,500 odds of existing simultaneously. And if you win that lottery, a journey that consumes 1/10 of your shared window before you arrive. The overlap that felt like salvation, the extraordinary coincidence of two civilizations burning at the same moment, is not rescued by proximity. It is drained by the crossing itself. But there is a question underneath all of this that has not yet been asked. Everything we have calculated assumes both civilizations have roughly the same window, roughly the same lifespan. What if that assumption is wrong? What if the problem is not just how long a civilization lasts, but how long the star itself is willing to wait? Because if the window of a civilization depends on the window of its star, on the star remaining stable long enough for life to arise, for intelligence to develop, for a civilization to crest, then the question becomes, what kind of star lives long enough to give that process more time? So the question becomes, what kind of star buys enough time? Because everything calculated so far assumes the star cooperating, stable, long-lived, patient enough for life to crawl from chemistry to complexity to the moment someone builds a radio telescope and starts asking whether anyone else is out there. If the star burns out before that process completes, the question is never asked. If the star's habitable window closes before the civilization has time to crest, the lottery ticket expires before it can be cashed. Start with our own sun, a G-type star, 10 billion years total lifespan, 4.5 billion already spent. That sounds like plenty of room, but life does not get the full 10 billion. The sun is gradually brightening as it ages, and the habitable zone is already migrating outward. Complex life on Earth has roughly 1 billion years remaining before rising solar output pushes surface temperatures past what multicellular organisms can endure. 1 billion years is enormous by human reckoning. On a galactic timeline, it is almost nothing. And here is the part that should unsettle you. We are not at the beginning of our window. We are near the end of it. Our whatever we are going to become, we have to become it now. The clock is not starting. It is finishing. Now look at stars more massive than our sun. F-type stars, roughly 1.3 times the solar mass, live 4 to 5 billion years. Earth spent 4.5 billion years producing complex animals. An F-type star would run out of time before an Earth-equivalent world could even reach the Cambrian explosion. The window is not merely shorter. It may be too short for the entire process to complete. Go larger still. A-type stars, twice the solar mass, live under 2 billion years. Under 2 billion years. Single-celled life persisted on Earth for over 2 billion years before multicellular organisms appeared. An A-type star dies before the story even begins. So smaller then, live longer, give life more room. Red dwarfs, M-type stars, are extraordinary in their patience. 0.1 times the mass of the Sun. They live for 10 trillion years. 10 trillion. The universe itself is only 14 billion years old. A red dwarf burns so slowly, so steadily, that it will still be fusing hydrogen long after every star like our Sun, has collapsed into a cold remnant. TRAPPIST-1, 40 light-years away, is a red dwarf hosting 7 rocky planets, at least 3 in the liquid water zone. When this argument considered red dwarfs earlier, the message felt like hope. Here is where that hope goes. A red dwarf's patience is also its cruelty. Because small stars are magnetically hyperactive, particularly in their youth, and their youth lasts billions of years, and they emit X-ray and ultraviolet flares at intensities that would strip the atmosphere from any nearby planet, sterilize the surface, destroy the ozone chemistry that complex life depends on. And because the habitable zone of a red dwarf is so close to the star, close enough for liquid water because the star is so dim, planets in that zone are tidally locked, one face in permanent daylight, one face in permanent night. The atmosphere circulates under extreme conditions, and the magnetic bombardment never fully stops. The star lives 10 trillion years, yes, but it spends most of those years making the neighborhood uninhabitable. The planet is alive. The civilization is extinct. That image stays with you, so neither extreme works. Too large, the star burns out before complexity arrives. Too small, yet the star scorches the surface for billions of years before settling. And the settling may come too late, or never fully come at all, which leaves K-type stars, orange dwarfs, 0.6 to 0.9 times the solar mass. They live 15 to 30 billion years, long enough for life to develop, calm enough to avoid the worst flare activity, slightly smaller and dimmer than our Sun, but within the range where rocky planets in the habitable zone could plausibly develop complex life. If any stellar type offers the temporal window a civilization needs, both to arise and to persist long enough to coincide with another, this is the most plausible candidate. And it still does not solve the overlap problem. A civilization on a K-type world, with 30 billion years of stellar patience behind it, still flickers through 1 million years of technological existence. The window problem does not change. The apartment building does not change. The 15 minutes of random tenancy scattered across a year do not become easier to coordinate just because the building has better construction. The timing remains the fundamental obstacle regardless of the landlord. But set all of that aside. Imagine the overlap exists. Imagine the energy exists. Imagine a ship launching toward a star 11,600 light-years away. At the fastest speed the physics of this argument has been willing to permit. The journey begins, and the destination moves. This is the part that never enters the popular imagination of interstellar travel. Stars are not fixed points. Yes, the Sun orbits the galactic center at 220 kilometers per second, completing one full revolution every 230 million years. Every star in the galaxy is moving. The one you aim at is moving right now, as this sentence is being spoken. In 50,000 years, the minimum plausible transit time for even the most optimistic speeds discussed here, the target star has drifted 37 light-years from where you measured it. 37 light-years. That is nearly 10 times the distance to our nearest stellar neighbor. And a journey of 500,000 years? 370 light-years of drift. But it is not even that simple, because the motion is not linear. Stars do not orbit in perfect circles. They bob vertically above and below the galactic plane on cycles of 60 to 70 million years, oscillating through the disk as the collective gravity of surrounding mass pulls them back and forth. The orbit itself is not a clean ellipse. It is a complex path shaped by every neighboring mass encountered over the journey, influenced by spiral arm crossings, by encounters with molecular clouds, by perturbations that accumulate over time in ways that are not fully predictable, even with perfect initial measurements. And here is 11,600 light-years for the last time. A journey of that distance, at 10% of the speed of light, takes roughly 116,000 years. During those 116,000 years, the target star moves. Not by a little, it relocates. And the coordinates you measured before departure describe where that star was, not where it will be. You would be firing not at a target, but at a memory. The trajectory you calculated on the day of launch is wrong. Before the ship has crossed a single light year, the error compounds over 100,000 years of flight. By arrival, the destination has shifted by an amount that would itself constitute a significant interstellar journey. You cannot aim at a star. You can only aim at where a star used to be. Every barrier in this argument has been a wall, distance, energy, time, temporal overlap, stellar lifespans. Each one closes a door. This one removes the doorframe. Even if you solved everything else, the target is not where the target is. Every barrier discussed so far, though, operates within a galaxy that is at least, and in some sense, navigable. The distances are vast. The energies are crushing. The timescales are civilization ending. But the target at least exists inside the same structure you do. It shares the same galactic neighborhood. The light from it reaches you. The math, however brutal, describes something real and local. But the universe is not one galaxy. It is 2 trillion galaxies. Surely somewhere in that almost incomprehensible volume, across all of that time and all of those stars, the barriers bend. Surely, at intergalactic scales, something becomes easier. Except, the universe itself is moving. And it is moving in a way that makes every barrier calculated so far look like a gentle inconvenience by comparison. Not the objects inside it, not the stars, not the galaxies, not the clouds of gas and ancient light. Yes, the space between things is stretching. Right now, while this sentence is being spoken, the fabric of the universe is expanding outward in every direction simultaneously, and every gap between every galaxy is growing wider by the second. Edwin Hubble published the proof of this in 1929. What he found was not that distant galaxies were flying away from us like debris from an explosion. What he found was something structurally stranger and far more threatening. The recession velocity of a galaxy is not set by its mass or its history or any property of the galaxy itself. It is set entirely by how far away it is. The farther the galaxy, the faster the separation. Distance determines speed, not the galaxy's speed through space. The speed at which space between us and the galaxy is being created. The number that governs this is called the Hubble constant, roughly 70 kilometers per second per megaparsec. A megaparsec is 3.26 million light years, which means for every 3.26 million light years of distance, space between us and an object is growing by 70 kilometers per second. Now run that forward. At 500 million light years, the recession velocity reaches roughly 10,800 kilometers per second, 3.6% of the speed of light, not 3.6% of some attainable velocity, 3.6% of the absolute physical maximum. Just from the expansion of space alone, before a single engine has fired, before a single gram of fuel has been spent. At 1 billion light years, the recession is 21,600 kilometers per second, 7% of the speed of light. At 5 billion light years, the recession velocity reaches 36% of the speed of light. Hold that. 5 billion light years is not the edge of anything. It is not even close to the boundary of what we can observe. And at that distance, the space between us and a potential civilization is already widening at more than a third of light speed, continuously, permanently, without any expenditure of energy, without any mechanism that can be countered or blocked or engineered around. A ship traveling at 35% of the speed of light toward a galaxy 5 billion light years away would not be getting closer. It would be falling behind. The destination recedes faster than the approach. And then 1998 happened. 2 independent teams of astronomers studying distant supernovae expected to find that the expansion was slowing down. Gravity is attractive. The mass of the universe pulling on itself should have been putting a brake on the outward motion, gradually decelerating the separation. What they found instead was the opposite. The expansion is not slowing, it is accelerating. The universe is not coasting outward from some ancient push. It is being driven, actively, by something that constitutes 68% of everything that exists. Dark energy. No one knows what it is. That is the honest answer. We have a name for it, and we know what it does, and we know how much of the universe it comprises, and we know almost nothing else. What we know is this: it does not dilute. As space expands and the volume of the universe grows, the density of matter and radiation decreases. More space, pay matter, thinner distribution. But dark energy does not thin. Its energy density remains constant even as the volume increases, which means, as the universe grows, the total amount of dark energy grows with it. This is the feedback loop that should unsettle you. Expansion creates more space. More space contains more dark energy. More dark energy accelerates the expansion. Accelerated expansion creates more space faster. More space, more dark energy, faster expansion still. The universe is not passively drifting. It is locked in an exponential cycle that compounds upon itself with every passing moment. The emptiness between galaxies is not a static desert that must be crossed. It is an active process, a widening, a thing that is happening to the universe right now as this sentence ends faster than it was when the sentence began. And here is where the compounding becomes architectural. Every barrier built so far in this argument assumed a universe that was, at minimum, standing still. Distances were vast but fixed. A journey of 100,000 years would cover 100,000 light years, however crushing the energy cost, however impossible the timescales. The target was not moving away while you were calculating how to reach it, but an intergalactic target is not standing still. It is receding, and the recession accelerates with every year that passes, which means every year you spend building the ship, every year you spend gathering the fuel, every year you spend traveling. The destination is farther, and the separation is growing faster than the year before. The target is not drifting. It is actively retreating, driven by a force that is 68% of the composition of reality itself. 97% of the galaxies within our observable universe are already receding faster than light, not 97% of distant galaxies. 97% of everything we can see right now from here. The universe visible to us is already almost entirely beyond reach. Not difficult to reach, not expensive to reach. Beyond reach in the way that a destination on the other side of a waterfall moving faster than any current you could ever generate is beyond reach. The expansion is accelerating. Every second, the threshold where recession velocity equals the speed of light draws closer to us. At some distance, today, space is widening at exactly light speed. And beyond that threshold, beyond that invisible boundary in every direction around us, the universe is already gone. What is that distance? But where exactly does the universe cross the point of no return? The threshold has a number, 14 billion light years. That is the Hubble radius, the distance at which space itself is stretching at exactly the speed of light. Stand at that boundary in your mind and watch what happens on the other side. Every galaxy beyond 14 billion light years is receding from us faster than light can travel. Not slightly faster, not marginally, frustratingly faster, faster, and accelerating. And the gap between their recession speed and the maximum velocity of any signal we could ever send is widening with every second that passes. And here is the thing about those galaxies beyond the Hubble radius. They are not gone yet. We can still see some of them. Light they emitted billions of years ago, when the distance between us was smaller. As has been traveling toward us long enough to arrive, we are seeing their past. Their present is already unreachable. The image in your telescope is a fossil. The source is already gone. Consider the cosmic microwave background, the faint radiation that fills every direction of the sky, the oldest light we can detect. It was emitted when the universe was very young, from a region of space that was, at that moment, roughly 42 million light-years away from where we would eventually be. That same region of space is now 46.5 billion light-years away. The expansion of the universe has stretched that original 42 million light-years by a factor of over 1,000. The light made it to us anyway, because when it was emitted, the universe was still young, and expansion had not yet accelerated into its current brutality. And that window is closing. It has been closing for billions of years. Now consider the full scale of what we are even discussing. The observable universe, the sphere, defined by how far light has had time to reach us since the Big Bang, is 93 billion light-years in diameter. That is not the universe. That is the visible fraction. The total universe, as best we can estimate, is roughly 250 times larger in diameter than the observable sphere. 250 times. Which means the volume of what actually exists dwarfs what we can see by a factor so large that the observable universe, from the outside, would look like a single mote of dust inside a cathedral. We see less than 1% of what is out there, probably far less. We will never see the rest, not because our telescopes are too small, and because the expansion has already carried it beyond any possible horizon. And the 93 billion light-years we can see, most of it is already lost. 97% of the galaxies in our observable universe are receding from us faster than light right now. Not the distant ones, not just the faint smudges at the edge of detection. 97% of everything we can observe. A light signal launched from one of those galaxies today, aimed directly at us, traveling at the full speed of light through local space, would be like a swimmer stroking against a current stronger than any stroke can overcome. It moves forward through local space at the full speed of light, and yet it falls farther behind with every passing second. The current is not just fast, yet it is accelerating beneath the swimmer's body with every stroke they take. Not for a long time, for eternity. That sentence should sit for a moment. Not for a very long time. Not until we develop better propulsion. Not until some future civilization solves the energy problem. For eternity. The word means what it says. Those galaxies are not destinations we cannot yet afford. They are destinations that have ceased to exist as destinations. The universe has not merely hidden them from us, it has unmade the possibility of ever reaching them permanently with no appeal by the operation of laws that hold everywhere in all directions without exception. So what remains? What does the universe look like from inside this shrinking sphere of possibility? The Virgo cluster, 50 million light-years away, yet it is receding from us right now at roughly 1,100 kilometers per second. That sounds large. Against the speed of light, it is a small fraction, but dark energy is not finished with it. In approximately 100 billion years, the Virgo cluster will cross the event horizon, permanently gone. The Coma cluster, 320 million light-years away, crosses it sooner, in roughly 80 billion years. These are not abstractions, these are specific objects with names that astronomers have catalogued and studied, and they each have a scheduled disappearance date written into the physics of the universe. Within 150 billion years, every galaxy outside our local group will have crossed the horizon. Every single one. The rest of the universe will vanish from us, not in a dramatic flash, but in a slow, accelerating fade, each galaxy redshifting toward invisibility before winking out of causal contact forever. And then the sky will be, for any civilization still watching, a much smaller place. What is the local group? It is roughly 80 galaxies, most of them small, gravitationally bound to each other closely enough that their mutual attraction overpowers the expansion. Andromeda is in it, 2.5 million light-years away. In 4 to 5 billion years, Andromeda and the Milky Way will merge, along with the rest of the group, into a single large elliptical galaxy. That structure, that merged remnant, will be our island. Not our neighborhood, not our region, our everything. The totality of what the universe will permit any future civilization to access, no matter how advanced, no matter how long they have had to develop. 80 galaxies out of 2 trillion. The universe is not slowly becoming inaccessible. It already is. We are living in a brief and closing window during which the light from other galaxies still reaches us at all, and that window shrinks by a predictable and accelerating amount with each year that passes. So think about where that leaves us. Every barrier raised so far in this argument, the energy, the time, the biological limits, the civilizational collapse, the galactic drift, every one of them operated within a universe that still, technically, contained other galaxies. What happens when you stack all of those barriers on top of this one? Now assemble the full architecture of isolation, every barrier stacked upon every other, and watch what the cumulative structure actually is. Start with the first wall, is spatial statistics. If roughly 10 civilizations exist in the Milky Way at any given moment, the nearest one sits approximately 11,600 light years away. Not because the universe is cruel, not because something went wrong, simply because 10 points scattered across 15 trillion cubic light years of volume produce that average separation by pure arithmetic. You cannot negotiate with arithmetic. The nearest neighbor is not closer if you want it to be. 11,600 light years. That is wall 1. But suppose you accept the distance. Suppose you commit to crossing it. You immediately meet wall 2. Special relativity does not merely limit how fast you travel. It restructures the geometry of the problem. As your velocity increases toward the speed of light, the energy required does not increase proportionally. It curves upward without ceiling. The mass of your ship, from the perspective of the universe, grows without bound. The speed of light is not a barrier you could break through with enough force. It is a wall that gets thicker the harder you push. No engine, no matter how exotic, circumvents this, because the law is not an engineering constraint. It is woven into the geometry of space-time itself, and wall 3 is waiting the moment you try to build the engine. The rocket equation has appeared in this argument before. It will appear here one final time, because this is where its full character becomes clear. It is a cage from which no chemical, nuclear, or fusion propulsion system can escape. Every kilogram of payload you want to move requires exponentially more fuel. More fuel means more mass. More mass means more fuel to move that fuel. The equation feeds on itself. At the velocities that make interstellar transit even theoretically feasible, the fuel-to-payload ratios become numbers with more zeros than the total mass of anything we have ever built. The cage has no door. It is the shape of momentum itself. So suppose somehow you slip past the first 3 walls. You have accepted the distance, accepted relativistic travel, accepted some hypothetical propulsion that sidesteps the equation in a way physics does not currently permit. You are moving. You are crossing the void. Wall 4 closes around you during the crossing. Civilizations are not permanent. The honest estimate of a technological civilization's lifespan, conservative, measured against the fossil record of mass extinctions, internal collapse, and the brutal improbability of sustaining complex institutions across geological time, is roughly 1 million years. That sounds long. Against the 13 billion year age of the galaxy, it is nothing. It is less than 0.1% of galactic history. The window during which a civilization exists and transmits and reaches is vanishingly short, and the probability that 2 windows overlap across not just space but time is not merely low, it is structurally near zero. For every 6,500 civilizations that ever exist, perhaps 1 pair shares the same moment. 1 pair. You could cross the void and arrive at a destination that was alive when you left, and is silent ash by the time you land. Not because anything failed, because the windows did not overlap, because they almost never do. But say the windows do overlap. Say your civilization and theirs both persist. Wall 5 has been building behind you the entire time. Stars move. The galaxy is not a static map. Every star orbits the galactic center at hundreds of kilometers per second on paths that span hundreds of millions of years. The target you aimed at when you launched is not where you arrive. Over a crossing of 50,000 years, your destination drifts roughly 37 light-years from the coordinates you used. Over a crossing of 500,000 years, nearly 400 light-years. And the star you are traveling toward has its own habitable window, a narrow band of time during which its luminosity and stability permit liquid water and complex chemistry. Stars more massive than our Sun exhaust that window in under 2 billion years, or often less. The universe does not hold the target still while you cross toward it. 6 walls, not facets of a single problem. 6 separate walls nested inside each other, each one catching anything that slips through the wall before it, forming a prison with no single point of failure. This is the architecture. Spatial statistics place the destination. Relativity caps the velocity. Thermodynamics and momentum make the engine an impossibility. Biology and existential risk make the civilizational window a blink. Stellar astrophysics moves the target and closes its own window. And then there is Wall 6. Dark energy is expanding the universe faster than light can cross it. 97% of all galaxies that exist have already crossed the cosmological horizon and are, in the only meaningful physical sense, gone. They're not distant. Gone. Unreachable. Not because we lack the technology, but because the space between us and them accumulates faster than causality permits any signal or ship to traverse. The remaining accessible universe, our local group, roughly 80 galaxies out of 2 trillion, is not a consolation prize. It is the totality of what physics permits to any civilization, anywhere, at any level of advancement, forever. Stack all 6, one on top of the other, and understand what the compound structure means. Passing Wall 1 does not bring you closer to meeting another civilization. It delivers you to Wall 2. Surviving Wall 2 delivers you to Wall 3. Each layer is independent. Each one is built from different physics, different timescales, different fundamental constraints. They do not weaken each other, yet as they do not share a common foundation you could undermine. The probability of surviving all 6 is not merely low, in the way that winning a lottery is low. It is low, in the way that a compound of 6 independent near impossibilities produces a result that rounds, structurally and honestly, to 0. There is no crack. There is no weakness in one wall that compensates for the strength of the others. The prison is complete. There is a temptation to receive this as tragedy, to feel the weight of cosmic loneliness pressing down on every upward glance at the night sky. But there is another way to hold this knowledge, and here is the other way to hold it, not as a sentence handed down, not as a verdict on human ambition, but as the cost of the receipt, at the itemized price of what it took to produce a mind capable of reading that verdict in the first place. Start at the beginning, not the beginning of this argument, the beginning. 13.8 billion years ago, everything that exists occupied a single region of incomprehensible density and temperature. No atoms, no chemistry, no time in any direction that a biology could navigate. Just plasma, undifferentiated and total. And then the universe expanded and cooled. And the cooling was not failure. The cooling was construction. Protons and electrons slowed enough to capture each other. Atoms formed. Simple ones first. Hydrogen, helium, and the same gravity that would eventually make interstellar distances so punishing pulled those atoms together into the first stars, where pressure and heat ran the nuclear reactions that forged everything heavier. Carbon, oxygen, iron. The atoms in your body did not arrive here by accident. They were manufactured in stellar cores over billions of years and scattered by stellar deaths across distances so vast they eventually seeded new systems, new worlds, new chemistries. That process took time. Enormous time. Not because the universe was inefficient, but because the physics demanded it. Nuclear fusion in a stable star cannot be rushed. The gradual accumulation of complexity, from simple chemistry to self-replicating molecules, to cells, to multicellular life, to nervous systems, to minds. Each step required the one before it, and each one required time that measured in hundreds of millions of years, 13.8 billion years, and that is what it cost to get here. Now notice something. The same laws governing all of that, the thermodynamics that cooled the plasma, the nuclear physics that forged atoms in stellar furnaces, the gravity that assembled those furnaces and held them stable for billions of years, those are not separate from the laws that impose the barriers. They are the same laws, identical. The thermodynamics that powered the first stars is the same thermodynamics that makes the rocket equation what it is. And here the rocket equation returns. One last time, not as a cage, not as a cruel mathematical fact that locks us in, but as a structural consequence, one more expression of the same underlying physics that made existence possible at all. And the reason you cannot carry enough fuel to reach another star at any meaningful fraction of light speed is the same reason stars burn for billions of years rather than exploding in an instant. The energy stored in matter is vast and it releases conservatively, according to rules that do not bend. Those rules ran long enough and stably enough to produce you. They are also the rules that make leaving prohibitively expensive. The prison and the cradle are the same room viewed from opposite directions. This is not a metaphor. This is the actual structure of the situation. The speed of light is not an arbitrary obstacle some indifferent universe has inserted to frustrate intelligent life. It is a fundamental feature of space-time, the conversion rate between space and time, baked into the geometry of everything that exists. Yet the same space-time geometry that allowed matter to cohere into stable structures over billions of years, that allowed stars to sit at fixed distances from planets long enough for biology to develop, that gave chemistry the stability to become inheritance, and inheritance the stability to become selection. That geometry is also the one that caps velocity and therefore inflates travel time beyond any civilizational lifespan. You cannot have the stability without the geometry. You cannot have the geometry without the speed limit. They are the same thing. The distances themselves, those vast, humbling separations between star systems, are not incidental. They are the reason stellar collisions are rare enough that solar systems can form and survive for billions of years undisturbed. Pack stars more densely and you sterilize the neighborhood. The gravitational chaos alone would eject planets from their orbits long before biology had time to begin. The emptiness is protective. The loneliness is structural. And dark energy, the force pulling the galaxies apart, the force that has already carried 97% of the observable universe beyond any possible reach, that same accelerating expansion is the thermodynamic condition of a universe that has been cooling and complexifying since the beginning. The universe we inhabit is not being destroyed by its expansion. It was built by its expansion. The cooling that created atoms, the diffusion that distributed matter, the eventual isolation of gravitationally bound clusters into their own permanent islands. All of it one continuous process, here from plasma to atoms to stars to biology to minds. To this moment, this exact moment, where one product of that process sits and attempts to understand the architecture of its own existence. The silence is not a wound in the structure, it is the structure. Every star that ever burned, every world that ever cooled, every ocean that ever formed, every molecule that ever self-replicated, all of it separated from every other instance of the same miracle by the same laws that made the miracle possible. The universe is not withholding. It built the conditions for life, and then, by the same physical logic that built those conditions, guaranteed that each instance of life would develop in isolation from every other, not as punishment, not as oversight, as consequence, as the unavoidable geometry of a process 13.8 billion years in the making. You are the result of all of it, not a bystander to the process. The plasma cooling into atoms, that is your history. The stellar nucleosynthesis, that is your biography. The billions of years of patient chemistry, that is your inheritance. And the isolation, the vast, permanent, physics-enforced solitude, that is the price written on the same receipt. And you have already paid it. You are standing on the other side of it. And here is what all of it adds up to. Not a warning, not a failure, not a flaw in the universe that a better physics might have corrected. What it adds up to is this. Every barrier we have traced, every wall nested inside every other wall, every law that compounds against every other law, all of it is the same process that produced the thing now trying to understand it. You are not trapped by the universe. You are made by it. The trap and the maker are identical. Somewhere out there, and we mean that literally, somewhere in the dark, beneath a sun we have not named, under a sky arranged with unfamiliar constellations, there may be a mind arriving at the same understanding tonight, and not through any signal we sent, not through any meeting we arranged, independently, the way all real discoveries happen, sitting with the same silence, running the same numbers, feeling the same weight lift when the weight finally stops feeling like loss. That mind is built from the same atoms, governed by the same constants, constrained by the same speed limit, the same thermodynamics, the same relentless expansion pulling everything apart at the seams. Whatever it looks like, whatever it calls itself, whatever sounds it makes when it speaks, it is, at the level of physics, the same kind of thing you are, a local arrangement of matter that became aware of the arrangement, a temporary structure that learned to ask permanent questions. You will never meet it. That is not changing. Yes, but the physics that separates you is the same physics that built you both. And there is something in that which is not loneliness. There is something in that which is closer to kinship than any meeting could provide. Look up tonight. Every point of light you can see is a sun. Some are near enough that the light reaching your eyes left within your own lifetime. Others left before you were born. A few left before any human being now alive drew their first breath. Those photons have traveled years, decades, centuries, and they are landing on your eyes right now, carrying information about places you will never visit and beings you will never meet. That light is the only message the universe sends, and it arrives constantly. The universe was not built for meetings. It was built for wonder, not as consolation, not as the thing you settle for when the real thing turns out to be impossible, as the actual design. Wonder is what happens when a mind made of 13.8 billion years of increasing complexity finally becomes complex enough to perceive the scale of what built it. It is not a reaction to the universe. It is the universe's most advanced operation. You are what the process looks like when it turns around and observes itself. The distances are real. The barriers are real. The silence is real. And it is permanent. And nothing we will ever build will change the geometry that enforces it. But you are also real. Right now, present in this exact moment, standing at the end of an unbroken chain that runs from a universe of pure plasma to a mind capable of grief about its own isolation. And that is not a small thing to be. And that is the most complex thing we have ever documented the universe producing. And it produced you, and the same receipt that itemizes the cost also confirms the delivery. So let the silence be what it is, not a wound, not an accusation, the quiet of a universe that spent everything it had building the conditions for something that could sit in the dark and understand why the dark is so vast, and feel something about it, and keep looking anyway. That last part matters, the keeping looking, because the universe did not guarantee wonder. It only built the conditions for it. You are the part that chooses to receive it. Go outside tonight. Let your eyes adjust. Wait for the sky to deepen into what it actually is. And when you see the first point of light appear, just sit with it for a moment. Not with what it means, and not with the distances, not with the physics, just with the fact that it is there, and you are here. And both of those things required the same 13.8 billion years of unbroken cooperation between every law of nature that exists. The universe traded contact for existence. You are the existence it bought.